Hello and welcome to Module 4 of Fabric Fundamentals. Today we're going to be discussing Delta Lake tables. Delta Lake tables are an open source storage layer that add relational database features to Spark. They're used in lakehouses and indicated by the triangle icon. Delta Lake tables are schema abstractions over Parquet files, and each table includes a Delta log folder for transactions logs in the JSON format. Key benefits are relational operations, so they support the full CRUD create, read, update and delete functions like traditional databases. They have ACID transactions, so it ensures atomicity, consistency, isolation and durability. Data versioning and time travel is available. That enables querying historical versions of the data, and batch and streaming support can be used as sources or sinks for streaming via Spark structured streaming. They also offer interoperability. Data stored in Parquet format is accessible via SQL analytic endpoints. We can create Delta tables. In Microsoft Fabric, they are created in the Lakehouse metastore, and data is stored in Parquet. Creating Delta tables from data frames, we need to use .write, .format, brackets, Delta, .save as table, and whatever you want to call your table in brackets. Manage tables stored data in the Lakehouse tables area, and files are deleted with the table. External Delta tables are created by specifying a path parameter. Data is stored in the files area or external storage, and deleting the table does not delete the files. When we create table metadata, we use Delta Table Builder, the API, to define schema and create empty tables. And we can use Spark SQL with create table using Delta for managed or external tables. Saving data in Delta format without the table definition, we use .write, .format, Delta, .save, and then the path to store data in the Delta format. It's useful for persisting transform data or preparing for later table creation. Write modes, we've got overwrite, which replaces all the existing data, and we've got append, which adds the new rows to the data. And we can optimize Delta tables. Spark writes new files for every update or delete due to Parquet immutability. This results in many small files, slow queries or failures, so we use optimize write. It reduces the number of files written by Spark. It writes fewer, larger files to improve performance. Enabled by default in Microsoft Fabric, and it can be toggled via Spark session, config, or table properties. We can use the optimize command, where we can consolidate small files into larger files, which improves on the compression and data distribution. Run via the Lakehouse Explorer or SQL, and the optional vorder can be applied for faster reads. And vorder optimizes Parquet files for fast in-memory-like reads. It's enabled by default and adds 15% write overhead. The benefits for Power BI, SQL, and Spark engines are not ideal for write-heavy scenarios like the staging area. We can use vacuum, and that removes old Parquet files no longer referenced in transaction logs. It helps manage storage and maintain performance, and the default retention of the vacuum is 7 days, and it can't be shortened. Partitioning the Delta tables, we've seen this in a previous module. We can organize the data into subfolders by column values, like the year 2024. Enables data skipping for faster reads. Best for large data sets with low cardinality partition columns. Avoid for the smaller data sets or high cardinality columns. When we're working with delta tables, we can use Spark SQL. So use spark.sql to run SQL commands in PySpark or Scala. It supports full CRUD operations, and we can use the SQL magic that can be used in notebooks for direct SQL execution. When we use the Delta Lake API, we've got delta table.for path to work with Delta files directly. It enables programmatic updates, deletes, and merges on Delta data, and it's useful for working outside the Lakehouse catalog. We've also got time travel and table history, where the Delta tables logs all the changes in the transaction log, and we can use describe history to view or change the history, change history. We can stream in Spark. Spark processes the batch and streaming data using the same API. Streaming is ideal for the real-time scenarios. The example, the Internet of Things data ingestion. And then Spark structured streaming. It reads continuous data from sources like network ports, Azure Event Hubs, Kafka, file system locations, and writes processed data to sinks, e.g. the Delta tables. Delta tables as a streaming source. We've got Delta tables can be read as streaming sources using read stream. Only append operations are supported unless ignore changes or ignore deletes is set. Use .isStreaming to verify the streaming status. And we can transform the streaming data using Spark functions to filter, add columns, and compute values. Write the streaming data to Delta tables using write stream. Use checkpoint location to track stream state and enable recovery. Query the output table to view process streaming data, or use .stop to end the stream and avoid unnecessary costs. So that was Delta tables. I'm not going to go through the exercise, but I will leave a link to it in the description. The only reason is it's another code heavy one, and that gave me a very long video last time, and really watching me copy and paste isn't too progressive. So see how you get on with that exercise. And if you have any questions, drop them in the comments. And of course, give a thumbs up and subscribe for Module 5. Thank you.